Hey everybody. All right, let's keep talking about electromagnetism. And last lesson was electric field, and we learned already with gravity that fields produce potentials. Right, so let's go same route. So let's go from an electric field to an electric potential in the same sort of analysis that we did with gravity. So let's talk about gravity. Remember when we had gravity using universal law of gravitation, this GMM over r squared, we were able to do a little bit of calculus. Did some integral calculus. Come up with this expression here for the potential caused by between two masses, the attractive potential. Remember that negative allowed us to talk about this as a force that will bring the masses together, right? Because it tells us that for us to increase it by a distance of r, it's going to be a loss of potential. So the potential increases as they come together, right? Or another way you could think of it is we had a reference point of negative. As we brought it to r, that's how we got that negative in there. Same idea works for electricity, because the Coulomb force, almost identical mathematical form to the gravity force. Now you can see them right here. This is the inverse square law of gravity. This is the inverse square law of electric charges, right? They're almost identical. So we can do the exact same analysis to come up with potential. Instead of it being m's and g's, we have k's and q's, but it ends up with the exact same mathematical form. The only difference now is the charge. Notice that we don't have a negative here, and it's because of the fact that we have the law of electric charges, that opposite charges attract and the same charges repel. So if we start with the same charge, if we multiply two positive numbers or two negative numbers, we're going to end up with a positive potential. What's a positive potential tell us? That means that it's going to require work to bring them together. They're going to repel. I had to bring two charges closer and closer together. They're going to fight each other. It's going to be a positive potential. We can think of it like if I'm starting off at some point and I want to bring it to a new point r, I have to go up the hill to fight that potential. If they're opposite charges, I'm going to have a negative potential, which means it's going to be going down the hill. Okay, so if I have call this like a point P, going to a point R, it's some arbitrary point P. I'm going to have a negative potential in that case because I'm going down the hill. In this one, it takes work to bring them together. In this case, it's going to take work to take them apart. Okay, we can think of it as sort of these hills going up or down. Very similar to gravitational potential. Maybe go back to those lessons. Check those out. See how that goes. Don't worry about the calculus bit, but this will give you a same idea here. Now, when we talked about a field, though, we didn't talk about Q1, Q2. We only talked about one charge. So let's keep going. So when we talked about potential in grade 9, way back in grade 9, we talked about it as a voltage. Right? We had a voltage in a circuit. We had this term electrical potential difference, which gave us an amount of energy that was being transferred by a charge, a coulomb of charge, through a circuit, through a piece of a circuit. We know how much voltage was lost at a light bulb, how much voltage was gained at a battery. In grade 11, we even talked about Kirchhoff's potential laws, that we had to split the voltage at a junction and come back together at a junction as well. All those ideas. Talking about voltage, talking about potential. What's the connection here between them? And the connection is we can now that we have these fields in space, we can completely get rid of the idea of just confining these voltages to the circuit itself. There are potentials around any charged object. Anything that has an electric field will also produce a potential, an electrical potential, that will then produce what we call a voltage. Okay? And it's going to be a voltage per charge, just like when we talked about an electric field being a force per charge. Remember we said that the electric field is equal to F divided by Q, we can now come up with a voltage being the same idea. If this is our potential formula, then our voltage formula will just be our potential formula divided by this test charge Q2. And it's going to come up with this expression here for voltage. Just like it looks very similar to the electric field equation, except it's not r squared. And in particular, this is not a vector. This is a scalar. This is a scalar potential, which makes the math much easier. When we add up these things, we don't have to add them as vectors. We can just add them as simple numbers. Okay? But now this is a voltage, but it's a voltage everywhere. It's not just a voltage in a conductor. Okay? Because a conductor behaves in a certain way because they conduct electricity, the voltage stays the same across any portion of the wire. So let's say we have a light bulb here and it goes into a battery or something like that. In this segment of the wire, my voltage will stay the same because there's nowhere for the energy to go. Right? We don't worry about it too much. The voltage stays the same. But there's actually going to be a voltage outside of it. We imagine some cross section here and we graphed that, we would actually end up with a electric potential as a 1 over r expression going away from it. So these potentials can exist outside of conductors. And we can attract things and we can do all kinds of fun things with that. So let's think about this for a second here. Let's do a couple of calculations. So let's see, we have a 5.5 microcoulomb charge and it's going to generate an electric field. Where are we going to find the higher potential energy? You don't even have to do any math to look at this. Is it going to be closer or farther away to have a higher potential energy? Remember, we're always going to be using our test charge. It's also always going to be 1 coulomb. So we have a positive charge, a positive 1, so they're going to repel. So the higher potential energy will have to be closer because everything's related to 1 over r. The closer I get, the higher the potential. If it was negative 5.5, do the opposite because it would be a negative potential. So we can just quickly do a calculation here though. V is equal to K U over R, 9.0 into the 9 Newton meters squared per coulomb squared multiplied by 5.5 microcoulombs all over 0.02 gives us an answer of 2.5 million volts. Or wait a second, I shouldn't say volts. Careful. All right, Newton. Okay, this was meters, so we'll cancel. Newton meters per coulomb. Is that a volt? Do the units work out? Always do. Let's just check. So a Newton meter per coulomb. What the heck is a Newton meter? That's going to be a kilogram meter second squared multiplied by meters all divided by coulombs, and that thing on top, that's a joule. So that's a joule per coulomb, which is a volt. Okay, so this is actually 2.5 million volts. Sounds like a heck of a lot, and it really just tells us what 5.5 microcoulombs is actually an incredibly large charge. Okay, so the electric potential 2 centimeters away from that charge is going to be 2.5 million volts. A lot. And but now, how much is that going to drop once we get to 6 centimeters? That's going to be 0.83 million volts. Okay, that's also volts. Okay, so it drops quickly, but yeah, just this is actually a very large amount. So don't worry about that number being excessively high. All right. So there's a quick little calculation. What's nice about this, I don't have to worry about vectors. There's no vector sign on this thing. We're good to go from there. All right, which makes this question much easier. When we did it with electric fields, we had to then break it up into components, add up all their components, and do that sort of thing. But when we're talking about this from a potential point of view, it's much easier. Okay, so in this case, again, I have a point here, D, and I'm asked to find out what the potential is here, given two positive charges over here at 10, 11-ish centimeters, and this one's 4 centimeters away. What's the electric potential going to be? We just have to do the same thing 3 times. So the voltage from point A, let's call that VA. That's going to be K UA over RA. That's going to work out. I'll let you guys do it, but it'll end up being 2.5 times 10 to the 6 volts. Okay, and once you work out VB, I got positive 9 times 10 to the, sorry, that should be 10 to the 5. So 9 times 10 to the 4 volts, and VC ends up being negative 6.75 times 10 to the 5 volts. Okay, and once I add all those up together, my total voltage is going to be VA plus VB plus VC. It's going to end up giving me a value of negative 3.4 times 10 to the 5 volts. Okay, there's my final answer, which is really nice because these are quite straightforward calculations we don't have to worry about. I didn't show all my work. Please check all my numbers to make sure they're okay, but I'm pretty sure it all works out here. Just be careful for VB. R is the square root of, or it's going to point, it's about 11 centimeters, so careful when you put that into the formula. Okay? Pretty straightforward calculation, don't want to waste your time, but please check the numbers. Pause right now, check those numbers. But once we have our number, let's think about what that means. I have a negative number, so what does that mean? At the point D, my potential is negative. So a positive charge stuck at point D, what's it going to do? So to do that, why don't we graph this? If I have a 3-dimensional graph showing this is done with a GeoGebra, a fun little program. I tried to share it. It doesn't want to share properly for some reason, but this is generating these potentials. And you can see the point here, this is point D, it has a value in the negative, which means that a positive charge here will be attracted to that closest negative charge. Remember, there was a negative charge here. Nope. There was a negative charge there. There was a positive charge at 10, and then another positive charge somewhere about there. Okay, and the influence of all those charges together, these positives weren't big enough to affect this enough. It's mostly still going to fall down the hill there. But you can imagine if this electric potential generates this 3-dimensional surface, which tells us whether or not a charge will be attracted or repelled. Right? If there's a charge here on the surface, it's going to be pushed away from that big positive 3 microcoulombs, and it's going to be attracted to this negative 3. Right? It's going to fall down the hill in this way. And there's going to be some point somewhere here, some surface here where it's going to go to 0. We can demonstrate the same thing using the FET charge simulation, and we can come up with this that shows these the red and the blue represented the voltage. It represented the voltage around those two charges, and the positive voltage really means it's a potential out of the screen, and a blue is into the screen. We can think of this as a 3-dimensional plot, and these lines we call equipotential surfaces actually represent what we can think of as contour lines. You remember from geography, when we had a mountain or something like that, we represented, we were able to show the elevation and the topography using what we called contour lines. So these circles here represent a surface or a line where there's the same potential. So at this point, this is the answer we got here. Well, it's off by orders of magnitude because it used nanocoulombs instead of microcoulombs, but you can see that we got 3.4, which is the same as we got for our answer, negative 3.4. at that point. But it also shows us that it's also this negative 34 volts all along this green line. Everywhere along there is the same voltage. So we can think of it as the contour line of the surface that has the same Z value. This axis here, the blue axis, the Z axis. We can think of these contour lines as being these equipotential surfaces. Go back to this charge simulation, add some charges, and play with this little equipotential. You just move the little cursor around. Now let's actually go there right now. Okay, so if I drop a charge here, it generated an electric field. Right? Put it somewhere. Generates this electric field like this, right? But I'm able to then generate the voltage as well, which shows this outwards potential. And then if I take my little potential sensor here, it'll show me what the potential is as I get farther and closer to that charge. And then I'm able to actually put it on so I know these dots. I can actually draw, pressing on the little pencil, and it actually generates my equipotential lines. And because this is 1 over r, it's going to be symmetric about r, and it ends up going to give circles. Now if I add another one, add a negative charge, and that's going to be a little bit more complicated, because there's going to be a very large gradient in charge in between them. They're going to be squeezed together in between. And so this again is these equipotential surfaces, we call them equipotential lines. Really, they're equipotential line here. It's surfaces in 3 dimensions. If I extended this 3 dimensions, I would have a sort of like a weird elongated or squished, maybe squished sphere that would all have the same potential around it. So why don't you go back to that simulation as well and play around with different configurations of charges and see what the equipotential lines do. Okay, so that's the solution to our problem here mathematically and using our simulation, and graphically. These aren't exact because this is using unitary, not using actual units. So you can see it, where is it? It's something like 0.3. Again, it's off by orders of magnitude, but let's not worry about it. What we also can do is, using this, is we can find out where the potential will be 0. So let's say I have a 5 microcoulomb charge, and it's 5 centimeters away from a negative 7 microcoulomb charge. Where is there no potential? Where's the 0 point between them? Okay? So what that means is we're going to have to add these things up, right? If we do a little graph just to think about what this means. So let's say, setting up our frame of reference, let's use our 5 microcoulomb charge as our frame of reference. And we're going to then have 5 centimeters away a negative 7 microcoulomb charge. So if I have my test charge, my positive test charge, close to my positive 5, I'm going to have some sort of positive value. So I'm going to have a positive number. And then as I get farther away, it's going to go away. But then once I get to the closer and closer to the 7, it's going to be attracted. I'm going to get some sort of an expression like this. And at some point here-ish, I don't know exactly, it's probably, actually I think I did that completely wrong. Let's think about that a little bit more, because this is a negative 7, but that one will have more influence. So it'll probably be closer to 2 than it is to 3 centimeters. Somewhere around here. But just completely completely guessing here, I'm thinking it's somewhere around 2 centimeters. Ish. Let's see if we're right. So how's this going to work? So for us to get our potential, let's call it U. Let's call it B. B, that's going to be the voltage from my 5 coulomb charge and the voltage from my 7 coulomb charge. Okay, they're going to be the same. Right? We're going to add them in the same fashion. They're just scalars. If I can just add them. Math just applies to scalars just like normal math. So what are we going to get here? We're going to get K, the charge on the 5 coulomb, which is 5, and the distance away from the 5 plus k charge on 7 divided by the distance away from the 7. And all of this is going to have to be equal to 0. What's nice about that, I can just divide everything by k. K's are gone. Now, this is going to be 5 microcoulombs. And let's just call it r. Let's just call the distance here r. We're using the 5 as our frame of reference. Let's use r as the distance away. R right now we're going to define as the distance from 5 coulomb. 3 equal signs with 3 lines. That means we're going to define it to. And then we can say use 7. Oh, sorry. Call that straight away 7 microcoulomb. Now, what's the distance away from 7 when we're r away from 5? Let's say I'm using 2. If I am 2 centimeters away from the 5, how far away from the 7? 3, right? So we could say then that this is going to be 5 take away r. Whatever distance I am away from my 5 microcoulomb charge is always going to be 5 centimeters, right? 5 centimeters here minus r. And I don't care about the fact that it's centimeters, because when I work out my answer, it's going to be in centimeters, and I've gotten rid of k. There's no units really that matter. I'll just get a nice value there. Now, all I have to do now is solve this expression here. So 5 over r plus 7 over 5 minus r. You guys can work that all out. We can cross multiply, right? What's that going to work out to? Wait a second. That's a negative, right? So when I work this all out, I end up with, I'll let you guys play with this. Should I solve it? Solve it for you guys? You guys are good at algebra. Right? This one comes over. Let me cross multiply. We get r by itself. I should probably do it, right? All right, so 7 over 5 minus r equals 5 over r. Cross multiplying, I get, over here, get 7r is equal to 25 minus 5r. Right, and then that means that 2r is equal to 25. Yeah, sorry, 12. Right, 12. 5 plus. And then that's going to be 25 over 12, which is, oh, look at that, it's about 2.1 centimeters, which is what we estimated. All right? Okay, so we can see here, this is just a simple algebra problem from here, and it's because of the fact that these scalar fields just add together. They're not vector fields now. This is a scalar field, which makes things much easier to deal with and gives us a nice simple answer. Okay? So again, as we talked about equipotential lines, these represent the lines where all the potentials are the same. And the only thing I didn't really say is that the equipotential lines and the field lines are always at right angles to each other. Always right angles everywhere, which makes sense. A field line represents where we're increasing the most. It's the direction in which we're going. Imagine if we have a hill. The contour lines of that hill, let's say a hill, I can have contour lines coming around it that represent equal heights, and the field lines represent the direction that you have to travel to go up the highest amount. Okay? This has some interesting things to talk about in terms of calculus, but we're not going to get into that. Okay, so just remember, equipotential lines, just contour lines on a map, or surfaces where all the potentials are the same. Okay, so pretty short homework today, just 3 problems. And again, these aren't that difficult because we're not adding vectors anymore. We're just adding up these the scalar fields that make math much easier for us. All right. Okay, so best of luck. I hope you guys are all doing well. It's almost May, which is incredible. My quarantine here is getting nice and long, getting closer and closer to the ideal Flint Lockwood. But hope to see you guys before September, but who knows? Best of luck, stay safe, do physics, and we'll be talking to you later.